Okay, so thank you, first of all, for the incredible introduction and even giving me the invitation in the first place to come along and speak to you all. So it seems a bit redundant to say it, but hi, I'm David, and yeah, my pronouns are he, him, and if you want to talk to me about any of the kind of stuff I blabber on about today, then there's plenty of like Twitter accounts or wherever you can find me. I'm easy enough to find online. But today I'm going to be giving you a talk in two parts. So the imaginative title of Seeing Magnetism and Sexuality in New Light. So first off, I'm going to talk about some work that I did during my PhD using X-ray sources, synchrotrons, to look at magnetic properties. And then the second part is going to be about my experiences coming out in Exeter and all of the support that I received during that process. Now, I should point out, there's a little bit of a typo that you've mentioned there, as I say, during promotion. I got to call myself out on this one. So yeah, that's pending completion of my thesis correction. So push this back a couple of months and that'll be, I can remove the slide. But okay, I think it's about time. Again, that's just lovely little image there I like to include, where it's one of my favorite images at the Diamond Light Source, which is UK Synchrotron Facility. And of course, it's got the rainbow, part of the reason why I love it, and it's just forms a large amount of my research. So that sigil crops up a lot in my life. And now let's try and kind of convince you that magnets are more than just kind of something you get your nan to stick on the fridge after you've been on a holiday. So magnetic materials are crucial for tons of electric and electronic devices, from motors that you see in your cars to hard drives in your computers or in your phones. And we started off early days of this work with just simple lumps of material. You have your iron or your nickel or something like that. And technology, it moved on. We started moving into composites. So state of the art became neodymium iron boron. And as technology has continued to advance along, nanofabrication in particular, being able to make things on such small levels, we can start trying to combine materials and create sort of layered structures like this example you can see here. So we can have several magnetically active layers. However, this in of itself provides a problem, because if you can read that, I hope that you can see there's an absolute mess. You've got cobalt, you've got iron, you've got copper, tantalum, ruthenium, iridium, manganese, and if we have all of those different systems kind of all interfacing, then we have to ask ourselves, when we're measuring or running the system, if we have a resonance that we don't like or some part of the system that is misbehaving, how do you know which atomic species it is? How do you know whether it's the tantalum, which is causing something weird, which means that you can't use it? Or how do you know if it's the iridium? So this is the question, really, but I just can't sum up there. How do we resolve the behavior of the individual layers? And if we do that, then we can make better magnetic materials for all of those applications that we mentioned in the first place. So I realized that I've got quite a broad kind of selection of the audience. So I'm going to take a step back and kind of, where does magnetic moments kind of really come from? So this is a simple atom, simplest one I could really come up with. So hydrogen-like, so it's got a single electron, and magnetic properties come from three sources of the atomic magnetic moment. So within the nucleus, which we have the neutral charged neutrons and positively charged protons, you have a nuclear magnetic moment. Now that is absolutely tiny. It's like 1/100th of the size of the other ones. So I'm not going to spend too much time talking about that, and you can just kind of ignore that one straight off away. And if I was smart, I probably would have had a nice little animation where that disappears. And then second, we have an electron kind of orbiting around with this nucleus. And this can be kind of, if you really want to kind of put yourself through that, you can derive this from Maxwell's equations, standard sort of transformations and such, where just angular momentum of a charged particle then creates this magnetic moment. And as well, this kind of helps with the next parts, but if you imagine that, it looks kind of like, hopefully someone will kind of imagine, looks kind of like the Earth orbiting the sun. Kind of, if you can see the sort of analogy that we're drawing there. So we have the nucleus, the sun, and the electron both orbiting around, which hopefully I don't need to convince anyone that that's the case. But okay, but then we have what we call going back to our atom here, we have what we call the spin magnetic moment. This is a misnomer because it doesn't actually spin, but it's more comfortable to lie and say that it can just call it spin than to try and work out, because if anyone can tell me in more detail, well, I look forward to hearing your Nobel Prize acceptance speech, because that's surely coming if you can explain. But basically, this is some intrinsic quantum contribution from the electron that adds into this magnetic moment. And for your total atom, this is the sum of all of these. And a couple of other little bits that will make sense there is electrons are what we call fermions. So these are type of particle and they have spin 1/2. And we often consider that they can have a spin up or a spin down. And they obey what we call the Pauli exclusion principle, which means that no two electrons can have the same quantum numbers and exist in the same position. It's kind of like the subatomic equivalent of, well, one of us is going to have to go change. So moving on from that, I can then try and build up with new scary words and to introduce to you the XMCD principle. So the XMCD acronym stands for X-ray magnetic circular dichroism, which is very much a word salad, which kind of translated as roughly the difference in absorption between different biomagnetic material of X-rays with different circular polarizations. Now, I apologize because this is going to be a scary image to look at right here. But I'll try and talk you through and just, if anyone really thinks that this is too simple, again, I will point you towards that entire chapter of the book there, and you can go nuts with that. But, and simply, as I say, we've got different circular polarizations of light, and here are the core electrons, so the most tightly bound, and we have spin up and spin down. Now, in a lot of materials, those are at the core, we have the valence band. Now, these are the outer electrons, and these contribute to like a good 80% really of the magnetic properties. And you start with this. So first part to kind of that you should take away is core electrons receive angular momentum from these incident X-rays. Then they couple to the electrons of the different subbands in a specific ratio depending on, as I say, whether they're spin up or spin down, and which angular momentum we have there. So this is, I know I have quantum physicists in the audience, so I will say this is a first order process, but I need to do this in 2 steps. So please do not come at me in the questions about it's not second order, okay? And then we have the second part of this. So just as we excite and transfer the angular momentum to the core electrons, they then get promoted up into the kind of Fermi band here, which is the highest energy kind of level that is occupied. And as you can see, hopefully from this diagram, if I drew it well enough, that there is a kind of imbalance of the number of available states between the different two. But that's how it works. And if none of that made any sense, that is completely fine too, because hopefully this is kind of what we get out of this. So we have the left and the right circular polarized light with the blue and the red. And with the dichroism, we take the difference of this and we can get a plot like this. Now, this is very useful for us because these energies that we observe there, so we've got the lower energy here and then the higher energy gap there. And these are quite unique for the different atomic elements. And so if we probe a system using these X-rays, we can look with a kind of focus on just that specific element because these are going to be different. So here it's for iron, nickel and cobalt will have different energies, like cobalt is 850 odd. So you can use these X-rays as a simple gauge. And here's my excuse to put some travel photos in as well. But the only places that we can really get such high amounts of X-rays as we need are these synchrotron facilities. And these are high-tech places where we can control fine parameters like the photon energy or the polarization. And there's about 70 of them around in the world. And we've got one in the UK, which is Diamond Light Source, as kind of Andrew mentioned during the intro there. And there's a picture of one of those. And then over in Berkeley, just across the way from San Francisco, so that's the Golden Gate Bridge, just for any keen geography nuts out there. And that's kind of the facility. So XMCD, we can use that to get static properties, right? But then we want to look at dynamics, because usually we care more about magnets when we're in motion and doing things. And this one, again, a little bit scary, but I'm trying to rush through this one a bit quickly. So the X-ray pulses are kind of come along over here in the synchrotron, sexually polarized at frequency of roughly 500 megahertz. So that's 500 million per second of these pulses. And we can also send out a master oscillator kind of electrical signal, which then kind of comes along to a comb generator, which outputs this into, kind of multiplies it such, but it's now in much higher frequency, which is more convenient or kind of more appropriate for looking at these magnetic properties. So we do that along, and we come along to sample. The X-rays come in, and you get different absorption depending on whether the energy matches the ones that I showed before in that plot. And then we can also excite that magnetization, so it's just kind of processing around like so. And we can detect it from any number of ways, including a photodiode behind the sample. If you want to detect, say, as things decay from the higher down to the lower energies, they'll have a cascade processes involving loads of electrons and different photons, and we can then siphon that away over at the lock-in amplifier. As I mentioned with this procession, we have two main parameters that we are free to vary. So we have the magnetic bias field, and when we get to resonance, we kind of open up that cone and we get a larger angle there, which you can sort of see on that plot of some example data being around 6 millitesla in this case. But the other thing that we can change as well is the delay between the RF and the X-ray probe. So my crew kind of former kind of tutor used to explain this as pump probe experiments, like if you push a cat off of the top of a roof, and then you can only take a snapshot of a very specific point, you need this to be repeatable, and then you can move the camera taking different points, and you can build up a complete image. So in this crude analogy, much more cruel than I, but you can then change the delay and probe the different parts of this procession, and that's how you get the whole sinusoid that we see over there. Now, I can talk about this all I like. Most people are going to ask, yeah, what's it actually good for? Or why should we actually care? So I'm going to bring this over to, here's one I measured earlier. So we have antiferromagnet systems, which I mentioned before, the magnetic moment. So we have ferromagnets where all of these moments in a larger sample are just aligned parallel together, but we can also get them aligned anti-parallel. And these are called antiferromagnets. And these have properties such as no magnetic moment and a high resonant frequency. And because of this has made them quite valuable as a potential magnetic data storage, because if you think with your current hard drives, one of the problems is if you try to shrink it too much, then you can have stray field, and when you try to write it with magnetic field, it ends up hitting some other kind of part, and you just end up causing loads of read and write errors. And then with the higher resonance frequency, we'd be able to get shorter time frames for those operations. So this would be faster, and we could make this as more dense data storage, which is fantastic. And another part of research directions in nanoscale magnetism is the idea that rather than our conventional electrical currents where we send an electron whizzing off down a wire, whether we could change this into more of a kind of like a game of whispers, really, with the electrons kind of passing along the spin angular momentum. And because of that, they don't create the kind of waste heat that we see in our magnetic data storage devices here. But this leads to a question that's been asked around of, does a spin current propagate through an antiferromagnet? And this has been a hard one to really work through, but we try to use this method by having a structure like this, where we create what we call a spin pump. So we excite this up into its resonance, and it wants to lose that additional angular momentum it gets at this point, and it will try to push that away in what we call a spin current. Now this will pass through the system, go through the nickel oxide, and then it will be kind of picked up in the iron cobalt. Now, this layer, or kind of these layers, and this one should have very different resonant kind of fields. So if we see something at the resonant field of this is called permalloy, by the way, just as I don't know why, but if we see something happening at the iron cobalt where the permalloy resonance is, then we can infer that this is the spin current being propagating through the system and driving it away and causing a peak when it's not at its own resonance. So doing these measurements, we can see, first of all, cone angle. So as I mentioned before about this cone widening up towards resonance. With the nickel, as we'd see in the nickel iron or the permalloy, it goes through its resonance. That's typical. And it goes through its phase of bipolar shape. There you go. Or a 180 shift. Again, that's typical. But then the fact that we can see a peak here in the cobalt, which is only found in the iron cobalt, which is entirely different from where its resonance means that we have a spin current and that this is kind of propagating through the nickel oxide. And if anyone really wants to run down the rabbit hole of this stuff, then there's the citation, and you can read through about what this means for antiferromagnets and how they really kind of, how a spin current propagates through them. Okay, and now that's me doing a word salad about the physics side. So we'll switch over to the second half, which I had to give it a name, of course, from polarizations to personal life. So more about my sort of LGBTQ plus journey. I wish that I could segue this better, but just please, I apologize for the jarring disconnect. We'll cycle around. So my partner, great love of my life, kind of discovered their true gender identity following lockdown. And this then led to me myself questioning some of the assumptions that I'd always had and had just been built in since growing up. Kind of sexuality or gender identity were not really discussed. It was one of those things where it's just, you assumed, you basically got told at birth, basically, you're a boy, you like girls, just there you go kind of live your life like that, whatever. So there wasn't really this ease of access to resources or for representation we see now of like all the different kind of ways that you can identify what gender can mean to you and what sexuality can mean to you. And I was originally going to have a slide with all of the lovely little kind of roles and such that we have now from TV shows like Brooklyn Nine-Nine, Dead End Paranormal Park, and all manner of Steven Universe, all of those sorts of ones, but I had to cut some slides somewhere, otherwise I just ramble on and on. So I started kind of having these questions and trying to rewrite or just understand more some of the experiences that I'd had in my life and what they really meant to me, and maybe looking at them kind of, I can maybe link this back down to the kind of theme, looking beyond the lens. See, we did it, there we go. So then this kind of came across with starting to reach out to local charities. So Intercom Trust, I'll say about them that they have helped me tremendously by they helped me arrange a counselor, Russell Martin, brilliant guy who helped me kind of talk through my feelings and realize that I think something that happens with a lot of bisexual people, that you kind of assume the default settings, as I always phrased it, that you can kind of fit well enough within the kind of heteronormative lens, really, that everyone else seems to be living with. So you just kind of continue like that and assume that if it ain't broke, right? But I realized that that wasn't all of me and that there was more to it than that. I wasn't just fitting into heteronormative. There was so many other feelings as well. And then kind of going through that journey with counselor, and thanks to Intercom Trust, I ended up coming out as bisexual, finding that to be the label that really fit with me most. And great coming out and feeling kind of more that I was like the body was a house, but I was actually seeing all of the rooms in it rather than just only living within a couple of them. So that was great, but I didn't really know people within the LGBTQ plus community. So then my partner suggested the local climbing group. So let's go belay and boulder together. And from that group, like a huge welcome. I've got a picture of them in there and the logo. And they really helped me with kind of learning what sexual orientation and gender identity and gender presentation means to other people. And from that, I managed to really learn what it means to me as well, from having seen what it is for other people. So that was really helpful. I met some wonderful people, and I'll never be able to really thank them enough for all that they've done. And also, I can now climb a bit as well, which is a nice little bonus to throw in there. But I will just kind of, now, personal side, you're probably happy to know, but I've stepped away from that research with the magnetism stuff now. So, but I'm not going to be talking to you about that too much anymore. And that I now do public engagement work. So for the Centre for Metamaterial Research and Innovation and the UK Metamaterials Network. And I know scary words, I love more of them coming out from me, but metamaterials are, in a simplest thing, these are kind of materials that get their properties by structure rather than composition. Like we have table there, it is wooden, and we have that because it's rigid, looks nice, all of those sorts of properties, those we get from its composition. However, if you were to make the right cuts within that, you can make it flexible. You can make wood that can bend and contort, and these are properties that it gets from its shape, from its structure, rather than composition. And that was a crude analogy, but we can then end up creating so many more. And if you really want to know this, I can send you to a video about a plasmonic tongue for whiskey tasting quality control. That's one of the ones which is apparently very big, but there we go. We'll discuss that one later. And yeah, sharing and promoting research now is more of what I do, including I was told to make the plug here for the British Science Festival, which is coming to Exeter this September. I believe the the deadline's already passed and people have heard whether they've been accepted or not for that. But even if you haven't been, I'm sure there'll be plenty of people asking for volunteers and try and do a whip round there. So I think that's probably enough out of me. So let's try and finish this up here. So on the magnetism side, hopefully discussed a bit about how the preferential absorption of X-rays in magnetic materials, depending on these polarizations, is a useful tool for looking at static properties, and that we can then expand on this and look at the dynamics. And then hopefully what I've also said about then more of the personal side is that if you are trying to figure out your sexual orientation or gender identity or any number of facets of your kind of what makes you you, then there are places that can help. There are people who can help. And it's never too late to find out new aspects of yourself. Like, you don't have to have it all figured out at 18 or leave high school having like a clear CV of, yes, I'm heterosexual, I am, or anything like that. You can find it as you go along. You don't need any set answers. And yeah, always try to find your community because, yeah, I think it's worth it. And yeah, another little prism dry photo in there. And yeah, thanks for listening.